Hi all. Hope everyone is staying healthy and happy out there in our socially distant world. So today I want to talk about approximation in mechanism design. And this is going to be the first time we bring computational considerations into our discussion of mechanism design. So just to recap maybe the last couple of lectures. 2 lectures ago, we gave and derived a number of nice properties for the VCG mechanism. And just to recap, the VCG mechanism was really able to solve in an extremely general setting lots and lots of mechanism design problems. And we showed that it was dominant strategy truthful, right? Nobody would have any incentive to misreport. It was individually rational. Nobody could come to harm by participating in the mechanism. It was social welfare maximizing. It always picked the solution that made everyone happiest in aggregate. And it was budget balanced. We, as the mechanism designers, didn't have to pay to run the mechanism. And so that was great. But last class, we sort of addressed one of the things that was sort of left to be desired by the VCG mechanism, which was that really it was tailor-made to maximize social welfare, right? Some player happiness. And we asked last class how far we could go retaining the properties of the VCG mechanism if the thing that we wanted to do was not to maximize social welfare, but instead to optimize some other objective or to run some other algorithm. And at least in single parameter domains, we were able to completely characterize the set of algorithms that you could pair with payment rules that would make them dominant strategy truthful. And we proved that if you wanted this truthfulness property, then it's not that you could do everything. It's not that you can get a generalization of the VCG mechanism that would optimize any objective that you like. What we proved is that you could do it if and only if, exactly when the algorithm that you wanted to run had this monotonicity property, by which we meant that if people bid higher, then the algorithm would only result in an outcome that was more preferable to them. So that's nice. In this lecture, I want to grapple with a sort of shortcoming of the VCG mechanism that is orthogonal to this. So in the setting that we're going to talk about in this class, social welfare is still the thing that we care about, right? We want to maximize aggregate happiness. And so if we lived in a completely computationally unconstrained world, the VCG mechanism would be the perfect tool for this. But our problem in this class is going to be that we only have finite computational resources. We're only able to solve polynomial time solvable problems. And so what this will mean for us is that we won't be able to run the VCG mechanism when social welfare maximization is an NP-complete problem, and we'll have to resort to approximation. And we'll have to be careful as we try to approximate social welfare that we do so in a way that doesn't give up the incentive properties that we're trying to design into our system. So just to sort of remember what the VCG mechanism does, it maximizes social welfare, right? And when we were deriving the VCG mechanism, we spent all of our time thinking about the payment rule. There was nothing interesting to do when it came to designing the allocation rule, right? Our hands were tied. The allocation rule, if we wanted a social welfare maximizing mechanism, had to always choose the alternative that solved this optimization problem. It had to choose the alternative amongst the set of all feasible alternatives that maximized social welfare. The problem is that sometimes that's easier said than done. So if we have a single item auction, this is sort of a trivial optimization problem. We just look at all the bids and we find the maximum bid. We give the item to the person who bid the most. Right, so in a single item auction, this is a trivial optimization problem. But as we start thinking about richer settings, for example, combinatorial auctions where people might have preferences over complicated bundles of goods, and the question is, how do we partition the goods so as to maximize social welfare? Or even more complicated things like the spectrum auctions that the Federal Trade Commission, or rather the FCC, ran several years ago to try to buy back spectrum from legacy users like broadcast TV stations, for those of you who are interested in prehistoric technology, and resell the spectrum to wireless carriers subject to all sorts of complicated combinatorial constraints imposed by the physics of radio interference. Very quickly, this problem of social welfare maximization can become incredibly complicated and infeasible to solve exactly because of computational constraints. So if you've taken an algorithms class, this problem that sometimes the exact problem that we want to solve is computationally intractable will not be new to you, right? This isn't only a problem when we care about incentives, right? Just as an algorithmic problem, there's all sorts of stuff we would like to be able to do, but that we cannot because we can only run for sort of a bounded amount of time with our finite computers. And there's a whole field that thinks about how to get around computational intractability like this. And one thing you can do is you can try to derive an approximation algorithm. For many problems, it's not so crucial that you find the exactly optimal solution. It's good enough if you find a pretty good solution, a solution that maybe gets, 95% of the objective value would be good enough for many purposes. And so, of course, we can try to do the same thing here. We can try to come up with approximation algorithms for our hard social welfare maximization problems. But the fact that we want our algorithms ultimately to be incentive compatible, the fact that we want to be able to pair them with payment rules that make truth-telling a dominant strategy is going to impose real limitations on us. And we know what those limitations are from last lecture, right? Like, we know that if we were maximizing social welfare, there would be a payment scheme, the VCG payment scheme, that would cause truth-telling to be a dominant strategy. But if we're running some approximation algorithm, we're doing something else. We're not quite maximizing social welfare. And from last lecture, we know that the only way we can possibly pair such an approximation algorithm with a payment scheme to make truth-telling a dominant strategy is if somehow we design our approximation algorithm to be monotone. And so that'll be a real constraint for us, right? Just to sort of remind ourselves like why this is going to be a problem, if you think back a couple of lectures ago to where we were proving all of these nice properties of the VCG mechanism, right? In particular, when we were proving that the VCG mechanism was dominant strategy truthful and individually rational, there were a couple of steps in these proofs in which we invoked the property that the allocation picked by the VCG mechanism was the one that exactly maximized social welfare. And these arguments and these properties of the mechanism are extremely brittle. So if we just try to use the VCG payment scheme without modification and swap in the allocation rule that exactly maximizes social welfare with some heuristic that even does a really good job short of exactly maximizing social welfare. For example, even if we swap in a heuristic that is always guaranteed to find a solution that achieves 99% of the optimal welfare, then these guarantees entirely break. They break sort of catastrophically. You can get sort of nonsensical things like negative payments. And so, this is why we really have to think hard. Achieving 99% of the optimal social welfare does not mean that if you use the same payment rule that you will in some sense be 99% truthful. You can entirely break the truthfulness and the individual rationality guarantees by seemingly only breaking the welfare maximization guarantees by a little bit. So this is a whole field, and in general, whenever you have a welfare maximization problem that you cannot solve exactly, and therefore you cannot use the VCG payment rule, if you want to design a dominant strategy truthful mechanism, you have to think about it, and you have to sort of design an approximation algorithm for your particular problem in a way that can guarantee truthfulness. And what I want to do in this class is sort of go through a case study of a particular example of this exercise. Okay, so I'm going to define on the next slide what are called knapsack auctions. These are a natural family of auction whose welfare maximization problem corresponds to solving what's called the knapsack problem. It's an NP-hard problem. And I'm going to walk through the process of how you might deal with this. And by the end of the lecture, we will have an approximation algorithm that not only guarantees a good approximation to the social welfare, but which can be paired with a payment rule that makes it dominant strategy truthful in a way that we wouldn't have gotten had we just used the VCG payment rule. So before I go on, are there any questions about sort of the premise of today's lecture? We haven't done anything technical yet, but this is a good time for sort of basic questions about like why do the guarantees of the VCG mechanism break if you can't exactly optimize things? Why is it that sometimes we can't exactly optimize welfare? Things along those lines. So let me know in the chat or by unmuting yourself if there's any questions. All right. So let me define knapsack auctions. And a knapsack auction is defined by a couple of things. We start with a collection of bidders, and bidders are going to have two properties, one of which will be public knowledge. We're not going to ask that the public part of their characteristic be reported truthfully, but the other of which will be private knowledge, and we'll have to incentivize them to report truthfully. So in a knapsack auction, each bidder will have a public size, okay? This is something that they can't lie about. And the mechanism has a public budget. Again, this is commonly known to everybody. The budget, again, is just some positive real number. We'll call it B. And the set of feasible alternatives are the set of all subsets of bidders whose cumulative size is less than or equal to B. Okay, so a set of feasible alternatives, the set of feasible alternatives is the set of winners we can choose. Okay, think about an outcome of this auction as choosing some of the bidders as winners. Some people will win the auction, some people will lose the auction. But I'm constrained to choose a set of winners whose total size, whose total resource demands, say, are less than my budget, B. And so notationally, even though the feasible alternatives, you can naturally think of them as sets of bidders, notationally I want to sometimes write them in terms of an indicator vector. So I'll think of an alternative A as being a vector of length n, where AI is 1 if bidder I is one of the winners and AI is 0 otherwise. Okay, so this is just notation to write, for example, a set as its indicator vector. And knapsack auctions are a single parameter domain of the sort that we studied last class. And that just means, I know ahead of time that everybody would prefer to be a winner than to be a loser. The only thing I don't know as the mechanism designer is how much they value winning an item. Okay, so every bidder will have some private, unknown to me as the mechanism designer, value for winning. That's just some number VI. That's the thing that I'm ultimately going to want to try to incentivize them to report truthfully to me. And their value for alternative A is just VI times AI, which is just another way of saying if bidder I is a winner, then they get value VI, otherwise they get value 0. Okay, so it's sort of a natural setting where people can either win the auction or lose the auction. They have some fixed value for winning. I don't know what it is. I need to get them to truthfully report it. And they get no value for losing. And this is a single parameter domain of the sort that we studied last class, which is going to be convenient for us because we know exactly what kinds of algorithms can be made truthful in single parameter domain settings. So the reason this is called a knapsack auction is because the social welfare maximization problem, which is just the problem of finding the feasible alternative that maximizes the sum of the values of the winners, is the knapsack problem that you might have come across in a class like 320 or 262, an algorithms class or a computability class. Right, it's the problem of finding the set of objects of maximum value that you can fit into some knapsack that has total capacity B when each of the objects I has some size WI. Okay, that's exactly what we're trying to do here when we're trying to maximize social welfare, because our set of feasible alternatives are exactly the set of bidders who collectively fit into a knapsack of size B. Okay, and this is an example of a social welfare maximization problem that is NP-hard, because the knapsack problem is NP-hard. And for our purposes, what that means is it's unlikely that we're going to find any polynomial time algorithm for solving the social welfare maximization problem. And so, we should be concerned at least about any plan that is going to try to just run the VCG mechanism to solve this problem at scale, right? The best algorithms for this problem are going to have running time that scale super polynomially in the size of the instance. And so eventually, if we get a large enough instance, we're likely to be unable to solve the problem. And by the way, this isn't an entirely contrived problem. The idea of having, needing to pick a set of winners who are constrained by some capacity constraint, and the different bidders have different sizes. This is actually something that comes up pretty frequently. So if you want to think about just sort of a mundane example of this kind of problem, think about selling seats on an airplane to people who have different size parties. Okay, so in this case, the budget is the number of seats on the plane. Okay, I cannot sell more seats than there are on the plane. The sizes of each bidder are the number of people they're going to travel with, right? So if I have a family of 4, I need 4 seats. I'm not going to be happy with 3 seats because we can't just leave my 2-year-old, at home. She doesn't know how to, open the refrigerator and cook food and stuff. Right, so we might have, bidders of size 1, they're traveling alone. We might have, a volleyball team all traveling together. There might be large bidders. And what I'd like to do is satisfy as many of the bidders as I can, like maximize social welfare, without needing to leave anyone behind. So, so the budget constraint's a hard constraint in a problem like this. Okay, so suppose we have to solve this problem. How should we go about doing it? What we need to do, right, is we need to find a choice rule which approximates the social welfare, right? We want to run in polynomial time. Exactly maximizing social welfare is NP hard, so that's sort of out of the question. So we need to find a choice rule that approximates at least the social welfare. Maybe that's not as hard as exactly maximizing it. And then I need to be able to try to pair it with a pricing rule that will make truthful reporting a dominant strategy. And because this is a single parameter domain, we proved last class exactly when that is possible. In particular, we know that we will be able to find a pricing rule that makes truthful reporting an approximate dominant strategy if and only if we can come up with an approximation algorithm that is monotone non-decreasing. Okay, remember, monotone non-decreasing just means that if someone raises their bid, they shouldn't go from being a winner to being a loser. So this is a sort of property that exact social welfare maximization naturally has, but it's not necessarily a property that all approximation algorithms would have. And because of last lecture, we can really just restrict our attention to the algorithm design question in this class, because we know that if our algorithm is not monotone non-decreasing, then we're out of luck. There's no payment rule out there at all that will make truthful reporting a dominant strategy. And the flip side of that is that if we manage to design an approximation algorithm which is monotone non-decreasing, we don't need any further cleverness to come up with the payment rule which makes truthful reporting a dominant strategy. We proved a theorem last class from which we can just read off a generic payment rule that we can pair with our algorithm that will make truthful reporting a dominant strategy. So you can think about last class as being an especially successful reduction in which we reduced an entire class of mechanism design problems that are defined in terms of incentive properties, and we reduced them to a purely algorithm design problem. And we're going to leverage that reduction this class, right? Like, we know now that the only thing we need to do to solve this auction problem is to design an algorithm that has a particular property, that has this monotonicity property. Okay, so let's fix some definitions. So first of all, what is the benchmark that we are trying to compete with? So an instance of the knapsack auction problem is defined by two things, right? For each bidder, I have to tell you what their valuation is, VI, and I have to tell you what their size is, what their weight is, WI. Okay, so an instance of the problem is defined by two vectors, V and W, which specify the valuations and the sizes of each of the bidders respectively. And our benchmark, which we'll call opt of V and W, is just the social welfare maximizing solution amongst all feasible solutions for that instance of the problem. So it's just the maximum over all subsets of bidders whose cumulative size is at most our budget of the sum of the valuations of those bidders. And with our benchmark in hand, we can define what it means for an algorithm to be an approximation algorithm. So we'll say that an algorithm A is an alpha approximation algorithm for the knapsack problem if for every instance of the problem, if for every possible vector of values and for every possible vector of weights, when we run the algorithm A on this instance of the problem, we get a solution out that, number one, is feasible, that it shouldn't violate our budget constraints. The solutions we get should always have their total size be less than our budget. Our algorithm should never try to sell more plane tickets than we have seats on the plane. And two, the algorithm should have the promise that the solution that it outputs is actually a good approximation to our benchmark opt. It should approximate the optimal social welfare to within a factor of alpha. Okay, so in particular, we want that the welfare of our solution, the sum of the valuations of the bidders who win in the solution proposed by our algorithm, should be at least the optimal solution for that instance of the problem divided by alpha. Okay, so if we have a 2 approximation algorithm, that means that our algorithm is always guaranteed to find a solution that achieves at least half of the optimal social welfare. If we have a 3 approximation algorithm, that means our algorithm's always guaranteed to get at least a third of the optimal social welfare. Right? In general, alpha is going to be some number bigger than 1. It's got to be bigger than 1 if it's going to be a polynomial time algorithm, because exactly optimizing is NP hard. And smaller values of alpha are better than bigger values of alpha. We would prefer a 2 approximation to a 3 approximation. Okay, any questions about approximation algorithms? Okay, and we don't want to come up with just any approximation algorithm, right? Like if this was an algorithms class, you know, we could end the definition here and we could go about trying to derive one, but it's not going to be enough for us to find an approximation algorithm, because not all approximation algorithms will satisfy this monotonicity property that we need for truthfulness. We need to design an approximation algorithm that has this additional monotonicity property. And let's just remember what monotonicity happens to mean in this particular setting. What it means is that for every instance of the problem, for every vector of valuations, and for every vector of weights, and for every bidder I, if bidder I considers over-reporting their value, if bidder I decides to report VI prime instead of VI, where VI prime is some bid that is larger than VI, then if I look at the set of winners that our algorithm comes up with when bidder I reports truthfully, and I look at the set of winners that our algorithm comes up with when bidder I over-reports his value, then if I wins when he reported truthfully, he should still win when he over-reported. Okay, the monotonicity property here means if you raise your bid, you might go from losing to winning, but you can never go from winning to losing. As a natural property, it's of course satisfied by algorithms that exactly maximize social welfare, but it is not necessarily satisfied by algorithms that that don't exactly maximize social welfare. And so our goal, our algorithmic goal here, is going to be to come up with a monotone algorithm that is simultaneously an alpha approximation for hopefully a small value of alpha for the knapsack problem. Right? Our goal for the rest of the lecture is sort of a purely algorithmic problem. There's no mention of incentives here, but of course we know from last lecture that if we can do this, if we can accomplish our goal, then we can read off the payment rule from last lecture that will, combined with our approximation algorithm, provide a dominant strategy truthful mechanism for approximating social welfare in knapsack auctions. And so in the rest of the class, I want to walk through a derivation of such an approximation algorithm. And so it's going to be helpful for us to write down our optimization problem as what's called an integer linear program. So let me describe basically the notation here, because there's nothing going on except a notation switch. Here's a way to write down an optimization problem that is just exactly our knapsack problem. Okay, except I'm writing it in terms of some linear objective function and some linear constraints. So here's the idea. we want to solve some constrained optimization problem over a set of n variables. The n variables here are these xi values, which are going to take value each either 0 or 1. And think about x as really just being the indicator vector for the set of winners in our auction. Okay, so the semantics of these variables are such that if xi is 0, that means that bidder I is not a winner. If xi is 1, that means that bidder I is a winner. Okay, so we're trying to solve for some solution over these variables xi. We're going to choose for each bidder I whether they win or whether they lose. Okay, and what we want to maximize is the sum over all of the bidders of xi times vi, right? The indicator for whether they win times the value that they get if they win, right? And so if you think about this for a second, this is just the social welfare objective, right? Because the people who don't win, their xi values are going to be 0. So their terms, the terms corresponding to their value will not show up in this sum. This will be a sum over all of the winners, right? It's only the winners whose xi values are not 0. It's going to be the sum over all of the winners of their valuation. So this linear objective is just the sum of the valuations of the people that we've designated as winners. So this is just the social welfare maximization objective. And our constraint looks similar. It's the sum over all of the bidders of xi, whether they win or not, the indicator of whether they win or not, times their size, wi. And we want this to be less than our budget b. And once again, what is this sum? Well, it's nothing more than the sum weights of all of the bidders that we designate as winners. Because for the bidders that we do not designate as winners, well, the xi values are 0, and so their term in this sum is also 0. And so this is really just the sum of the weights of the winners. And so what we're asking for is to find some solution, some subset of the bidders who are going to win the auction to maximize the welfare of the solution we pick, subject to the constraint that the solution that we pick is feasible, subject to the constraint that the set of winners we pick is has total size that does not exceed our budget. Okay, so ask questions if this is confusing, but I've done nothing here except rewrite our optimization problem in this linear form. I've got a question. Can you explain wi again? How does that manifest for each person and with respect to b? So remember in Knapsack Auctions, each bidder has some size. And so again, maybe like a good use case to keep in mind is selling airline tickets. So think about for each person who wants to buy some collection of airline tickets, wi is the size of their party, right? If I'm a sports team, maybe I want to buy 15 tickets. If I'm a family of 4, I want to buy 4 tickets. If I'm a business traveler on my own, maybe I just want to buy 1 ticket. And here, B would be the total number of seats on the plane. And so the constraint says, I want to pick some subset of people to sell airline tickets to, but I need to sell tickets to their whole party, right? It's not helpful to you if you're a family of 4 if I tell you, here's 2 tickets, leave your kids at home. And so the constraint is that I want to find the set of bidders that number 1 is feasible, the sum of their sizes, wi, doesn't exceed my budget, b, the number of seats I have on the plane. And subject to that constraint, I'd like to find the welfare maximizing solution. Does that make sense? Great. Good question. If there's any other questions, it's a good time to ask. All right. So, of course, I didn't, all I've done is I've written down our original problem in different notation. So I haven't done anything to it. And so of course, solving this integer program is NP-hard. In fact, right, like the fact that I can express the knapsack problem as an integer program is a proof that integer programming is NP-hard. So, number one, of course, I can't just solve the integer program. That can't be my algorithm. But number two, and this is sort of like a meta point that comes up a lot in theoretical computer science. One obstruction to coming up with an approximation algorithm and proving that something's an approximation algorithm is that we really need to be able to somehow get our handle on the structure of an optimal solution, right? Because ultimately, if I'm going to prove that some algorithm is a two approximation algorithm, I need to prove that whatever solution my algorithm comes up with achieves the objective value within a factor of 2 of the optimal objective value. So ultimately, I need to prove a theorem about the optimal objective value of every instance of a problem, which means that somehow in the workings of the proof, I need to understand some structure about optimal solutions. And as a general rule of thumb, the optimal solutions to NP-hard optimization problems just don't have any nice structure, right? This isn't quite a theorem, but if optimal solutions had nice structure, then we could come up with algorithms for finding them. And there are no good algorithms for solving NP-hard problems. And so as sort of a general rule of thumb, it's also very hard to find any structure in the solutions to NP-hard optimization problems. And so this is going to be a problem for us, and is generally a problem that you have to overcome when you want to come up with an approximation algorithm. How do you get a grip? How do you get a handle on optimal solutions that you have to ultimately prove theorems about without them having any nice structure? And so what we're going to do is we're going to, as an intermediate step, consider the following relaxed version of the problem called the fractional knapsack problem that does have nice structure. Okay, so here's the fractional knapsack problem. It's the solution to this linear program. And note that it is exactly the same as the integer linear program on the last slide, with one difference. The xi's no longer have to take values either 0 or 1. They can take any value, any real value between 0 or 1. Okay, so that's the only difference. We're maximizing the same objective, the sum of the xi's times the vi's, subject to the same constraint. The sum of the xi's times the wi's has to be less than or equal to b. The only difference is that now each xi doesn't have to be either 0 or 1. I could set an xi to be 0.2 or 0.9. Okay? And this turns out to make a lot of difference. So first of all, this is no longer an integer linear program. This is what's called a linear program. And this small change from requiring the xi's to be either 0 or 1 to allowing them to be any number between 0 and 1 is very important computationally. It means that this problem is no longer NP-hard. In fact, there are good polynomial time algorithms for solving linear programs. Now, we're not going to make use of that. We're not going to actually solve this linear program, because after all, it's not clear what we would do with a solution to it, right? Like, this is no longer the problem that we want to solve, right? Like, because the solutions don't correspond to sets of winners when the xi's can be fractional, right? Like, if I'm trying to sell airline seats, I'm not allowed to say, here's, a third of an airline seat, please pay me a third of your money. That wouldn't be a good solution. But even though we don't have any interest in solving this problem, it turns out that the optimal solution to this problem has some very nice structure, and we can make use of that. Okay, so this maybe seems like there's some sleight of hand going on here. All of a sudden, I'm talking about a different problem which seems different in only a very subtle way. The only difference is the xi's are no longer required to be integer valued. They can now be real valued. And all of a sudden, the solutions to this problem, this sort of relaxed problem, are going to have a very simple structure. And we'll see, in fact, there's a very simple algorithm for solving this problem. And we'll have to figure out how to use that because, of course, this is no longer quite the problem that we care about. Okay, but there's something, sort of deep going on here, which is that we're switching from a computationally hard problem to a computationally easy problem because we want structure. Computationally easy problems have structured solutions. Computationally hard problems do not. Okay. So this is some different problem. It's the fractional knapsack problem. It's not the original problem we cared about, which we'll call the integer knapsack problem. But it's some optimization problem. It does have some optimal solution. And so let's just write some notation to refer to this optimal solution. We'll write opt f for v and w to denote the optimal solution to the fractional knapsack problem, given an instance of the knapsack problem defined by a vector of values v and a vector of weights w. And again, this isn't the problem we want to solve, but we want to use the structure that it has as some intermediate part of our argument. And first, I want to observe something pretty simple, which is that although the fractional version of the knapsack problem is not the problem we want to solve, it at least has some relationship to the problem we want to solve. And so the first thing I want to observe is that for any instance of the knapsack problem, for any vector of values v and for any vector of weights w, if I look at the optimal fractional value of the knapsack problem on this instance, it can only be bigger than the optimal value of the integer knapsack problem. It can never be smaller. Okay. And the reason is because, remember, the fractional knapsack problem is a relaxation of the integer knapsack problem. That just means the set of feasible solutions is only less constrained, right? The solutions have to satisfy exactly the same budget constraint, but the integer knapsack problem has this more stringent constraint that the xi's have to be either 0 or 1, whereas the fractional knapsack problem has the more relaxed constraint that the xi's can be any number between 0 and 1, including 0 and 1. And so in particular, if you give me the optimal integer solution to the knapsack problem, right, the integer knapsack problem, that is a feasible solution to the fractional knapsack problem. It satisfies all of the constraints. It satisfies the budget constraint, and it satisfies the constraint that all of the xi values are between 0 and 1, because after all, they are either exactly 0 or exactly 1. So it is a feasible solution to the fractional knapsack problem. It's not necessarily the optimal solution. There might be a better solution to the fractional knapsack problem that takes advantage of the freedom to set the xi's to be non-integer values. But because it's a feasible solution, it means that the optimal solution to the fractional problem is at least as good. The optimal solution cannot possibly be worse than the optimal solution to the integer problem, because you could have always used the optimal solution to the integer program. Okay, does that make sense? So because this sort of fractional version of the problem is only less constrained than the integer version of the problem, we can sort of order these objective values. The optimal fractional value can only be bigger than the optimal integer value, not vice versa. We don't know how much bigger it can be, but it can't be smaller. Okay, any questions about that? This is going to be important for us because we're going to start reasoning about how well our solutions are going to do compared to the optimal fractional solution, which we're going to be able to reason about because it'll have some simple structure. And it's this inequality that's going to allow us to relate that to how well we're doing according to the, as compared to the optimal integer solution. right? So sort of the point here is that because the optimal fractional value, the optimal fractional solution to the knapsack problem is only better than the optimal integer solution, then if we can provide, say, a 2 approximation to the optimal fractional objective value, then we will also have obtained at least a 2 approximation to the optimal integer value 1, right? Because if we get some feasible solution that achieves objective value, opt f over 2, well, opt f is only bigger than opt, so it'll also achieve objective value at least opt over 2. And it's going to be easier for us to prove a theorem saying that we get objective value at least opt f over 2, even though that's a harder benchmark to compete against because opt-f is larger. And the reason is because the optimal fractional solution has very simple structure. And in particular, this is going to be the key piece of structure. Okay, so let me explain this lemma and its implications, and then we'll prove it. So suppose we have some solution to the fractional knapsack value, to the fractional knapsack problem that is optimal. Okay, so I solve the fractional knapsack problem, I get the sort of social welfare maximizing solution, and that solution is X. Then I claim that if I take any 2 agents, I and J, and when I look at the value density of bidder I, right? By value density, I mean the value of bidder I divided by the size of bidder I. And that happens to be larger than the value density of bidder J, then it's got to be that if I'm allocating anything at all to bidder J, I have to have fully allocated bidder I. Okay, so what this is saying is that the optimal solution can never allocate anything at all to bidders that have low value density, that have a low value of their V, of V over W, right? The density of their value. We can never allocate anything to sort of low density bidders until it has fully allocated the demand of all of the higher density bidders. Okay, and it's sort of telling us something about the structure that an algorithm for computing the optimal solution must have, right? It must sort bidders by their value density, right, by VI over WI, and then greedily start allocating capacity in order of this value density. Because if it does anything else, it'll result in a violation of this property, that there will be some lower density bidder J who will receive some allocation before bidder I has been fully allocated. And that's what this lemma is saying cannot happen. Okay, so we're going to prove this lemma on the next couple of slides, but this is going to be the key piece of structure we use about these fractional solutions. So if you have any questions about what this lemma means, what the structure is, now's a good time to ask. Okay, so let's prove the lemma. So suppose it wasn't true, right? Suppose we had such an IJ pair, so bidder I actually has higher value density than bidder J, but in the optimal solution, bidder J gets allocated something, right? Xj is strictly positive, and bidder I, the higher density bidder, is not fully allocated. Xi is less than 1. What we're going to try to do is we're going to try to perform a little bit of surgery on this supposedly optimal solution. We're going to try to change it a little bit without violating the feasibility constraints so that we have another feasible solution, but so that we've increased the objective value. And that's going to be a contradiction if we can do it, because the sort of premise of this whole thought experiment is that X was an optimal solution, right? If X is an optimal solution, there cannot possibly be another feasible solution that has higher objective value. Okay. So let's define this quantity delta that we're going to use in this surgery that we're going to perform on the solution. And I want delta to be the smaller of the following two quantities. I want it to be smaller than xj, okay? But I also want it to be smaller than 1 minus xi, weighted by the ratio of the size of bidder I to the size of bidder j. And note a couple of things. Like in particular, whatever delta is, it's strictly positive, because both of these terms are strictly positive, right? Like on the one hand, by assumption, xj is positive, so the second term in the min is positive. But on the other hand, xi is strictly less than 1, which means that 1 minus xi is strictly bigger than 0, and that remains the case when we multiply it by any positive number. Okay? So we don't exactly know what delta is, but we do know that whatever delta is, it's strictly positive. Okay? Like because of the assumptions going into the beginning of our proof by contradiction here. And so our plan is to use this value delta to somehow concoct some new solution x prime that is still feasible. Like we don't want to break any of the feasibility constraints when we perform our surgery, but we do want to rig things up so that x prime has higher objective value than x, and that is going to be our contradiction, because the assumption is that x is the optimal, x is the optimal solution. It's the feasible solution that has largest possible objective value. And so here's how we're going to do it. So all of the action in our surgery is going to happen between the allocations of bidder I and bidder j. Right? Basically, we're going to try to shift some mass from j over to I. And so for every bidder L other than I and j, x prime is going to look exactly like x. All right, like x prime of L is just going to equal x of L. We're not messing with anyone's allocation except if your name is I or if your name is j. And we're going to do something extremely intuitive, right? Like we're going to try to shift mass from the lower density bidder to the higher density bidder, right? That's intuitively the thing that you want to do, right? Because, for every infinitesimal unit of good that I give to bidder I get more welfare than for the same infinitesimal unit of good that I give to bidder j, because somehow the value density in bidder I is higher. And so here's how we're going to do it specifically. We're going to take xj's allocation in this purportedly optimal solution, right? So we're going to take xj, and we're going to reduce it by delta. So xj prime is just going to be xj minus delta. And then we're going to increase bidder I's allocation by as much as we can without violating the feasibility constraints. And what that's going to look like is we're going to take xi's allocation in this purportedly optimal solution, and we're going to increase it. And how much are we going to increase it by? Well, we're going to increase it by delta times the ratio of bidder j's size to bidder I's size. Okay, so this, these expressions shouldn't be transparent to you yet. It's not clear yet maybe why I'm increasing I's allocation by exactly this amount, but we'll see that this is what we need to do to satisfy our feasibility constraints. So the first thing I want to do is I want to observe that by performing this surgery, I haven't changed the size of the bundle at all, right? So that, we want to prove that x prime is still feasible, and there's two different things we need to prove, because there's two different kinds of constraints that define feasibility. right? First, there's the knapsack constraint. We need that the sum of the xi times xi times wi's, right? The total size of this fractional solution should not exceed b, and we need to make sure that's not violated by our little surgery here. And second, and we'll have to check this next, we need to make sure that none of the xi prime values are negative, and none of the xi prime values exceed 1, right? Because the other constraint is that the xi prime values have to be between 0 and 1. And so first, let's just verify that we haven't changed the size of our bundle. Okay, so we've increased i's allocation and we've decreased j's allocation, but I and j have different sizes. So let's think about how much we've changed the size of our overall bundle. Well, how much did we increase i's allocation by? Exactly by delta times wj over wi. That was the change in the allocation to bidder I. But of course, bidder I has some size, and so by increasing bidder I's valuation by delta times wj over wi, we've increased his participation in the knapsack by that times his size, times wi. Okay, and of course there's a cancellation here, right? So delta times wj divided by wi times wi is just delta times wj. So we've increased bidder I's participation in the knapsack by exactly delta times wj. On the other hand, we've subtracted off delta from bidder j's allocation, which means the total size we've removed from the knapsack is delta times wj, bidder j's size. And so we see that the total change in size of the bundle is 0. We actually haven't changed the size of our solution at all, because on the one hand, we've added delta wj weight to the knapsack. That's now new weight that is contributed by bidder I, but we've removed exactly the same amount of weight, delta times wj weight, that had previously been contributed by bidder j, and so the total change in the size of the bundle is exactly 0. And remember, x was the optimal solution, was nominally the optimal solution to the fractional knapsack problem. And in particular, that implies feasibility, right? So if x was feasible, if x satisfied the knapsack constraint, and by moving from x to x prime, we haven't changed the total weight of the solution, then it must be that x prime also satisfies the knapsack constraint. And so we've verified that by performing this little bit of surgery, we haven't caused our new solution to exceed the size of the knapsack. The sum of the weights, hasn't been made to exceed our budget B. And the only other thing we need to check to make sure that we have feasibility is that by performing this surgery, we haven't made any of the weights negative and we haven't made any of the weights exceed 1. And of course, we only need to check this for 2 weights, the 2 weights we modified, I and j. So we made j smaller, right? We subtracted delta off from j. And so we need to make sure that we haven't made that negative. Now remember how we defined delta, right? Delta is the minimum of 2 things, but in particular, delta can only be delta can only be smaller than xj, right? Because delta is the min of something and xj. And so we started with some positive number, xj, and we subtracted off from it some number delta, which is only smaller than xj. And so xj prime, whatever it is at least xj minus the largest value that delta can possibly take, which is xj. And so it's at least 0. So we subtracted something off from xj, but we didn't make it negative, which is good because we didn't violate feasibility. And then we added something to xi, right? We added this delta times wj over wi term to xi, and we need to verify that we didn't make this bigger than 1. But we're okay, because again, let's look at how delta is defined. It's the minimum of these two terms, and one of the terms is 1 minus xi times wi over wj. So we also know that delta is smaller than this term. And so in particular, delta times wj over wi shows up here. We know that xi prime is less than xi, and we can plug in our other upper bound on delta. Right, it's less than xi plus 1 minus xi times wi over wj, because we know this is an upper bound on delta, times wj over wi, right? And so the wi over wj the wi over wj cancels with wj over wi, and we're left with just xi plus 1 minus xi, which is equal to 1. Okay, and so we also haven't screwed up there. Like the amount of weight that we added to bidder I has not caused its allocation to exceed 1, and so we still satisfy our feasibility constraints. Okay. So by doing this, we've come up with a feasible solution. And the last thing we need to argue to arrive at a contradiction is that our solution actually has higher objective value. And if we can do that, that'll contradict the premise that X was the optimal solution. Right, so what we need to show is that the change in objective value, and remember, what's the change in objective value? Well, we subtracted something from J's allocation. We subtracted delta from J's allocation, so we've lost delta times Vj in objective value. But we've also gained something, right? Because we added to I's valuation, sorry, we added to I's allocation. We added delta times Wj over Wi to bidder I's allocation. And so we gained delta times Wj over Wi times Vi in our objective value. And we need to argue that this is positive. We need to argue that we actually increased the objective value. But this is the case, because remember, what was the starting premise here? The starting premise was that bidder I had higher value density than bidder J, right? All that means is that Vi over Wi, the density of bidder I, by assumption, is bigger than Vj over Wj. Okay. And so let's just multiply both sides of this by Wj, right? Algebraically, that's the same thing as the fact that Wj over Wi times Vi, right, the amount that we're adding to our objective value, is bigger than Vj, the amount that we're subtracting from our objective value. Okay, and so the amount that our objective value has changed has been strictly positive. And that's a contradiction, because if we truly had the optimal fractional solution X, there would be no way to get another feasible solution that had higher objective value. Okay. So what can we do with this structure? Like, what does it mean that, what's it going to mean for us that optimal solutions have to have the property that higher density bidders are fully allocated before lower density bidders? Well, what it's going to mean for us is that we can get a combinatorial characterization of the optimal solution, right? Like, the only way you can possibly find an optimal solution is by running the following sort of obvious greedy algorithm once you understand this structure, right? Like, what you have to do to come up with an optimal solution is sort the bidders in decreasing order of their value density. We have to sort them by their value density, Vi over Wi. And then we just have to start allocating these bidders in decreasing order of their value density until we run out of budget, right? Because if we do anything else at all, that will result in some lower density bidder getting an allocation before we've fully allocated some higher density bidder. And so what we previously had, this hard to understand solution to an NP-hard optimization problem, like, it's now this simple greedy algorithm. We just sort the bidders in decreasing order. We keep track of, who we've allocated, like who we've decided has won, and the size of the size of our allocation so far, initially 0 before we've allocated anyone. And we just do the following greedy thing. In order, in decreasing order of value density, we ask for each bidder, is there room for them in the knapsack? Like if we added them to the knapsack, would we still not exceed our budget? And if there's room to them, we'll allocate them to the knapsack and we'll do the necessary bookkeeping. We'll record that we've added them to the knapsack, and we will add their weight to the running size that we're keeping track of our solution. And we'll keep doing this until eventually we get to some bidder I who doesn't fit into the knapsack. We get to some bidder I that we cannot fully allocate because, given the partial solution we've constructed so far, if we allocate this bidder I, we will exceed our budget. Now, we might not have entirely run out of space in the knapsack just because the next bidder can't entirely fit into it. There might be some fractional bit of the knapsack that is left. And because we're only trying to solve the fractional knapsack problem, that's okay for us. So what we'll do then is, for this last bidder I, the one who doesn't quite fit into the knapsack, we're just gonna fractionally put in whatever part of them does fit. So we will allocate to bidder I exactly the remaining space left in the knapsack, which is just, that just means that their allocation will be the remaining space in the knapsack divided by their size. Okay? And after we do that, the knapsack will be full. And so anyone who comes later in this ordering, in this value density ordering, won't get allocated. We'll have to set xj to 0. And that's it. This is the only way you can possibly come up with an optimal solution to the fractional knapsack problem, given the structural lemma that we proved. And so now we have an algorithm for the fractional knapsack problem. And the question is, can we use it to get a solution to the integer knapsack problem? And one observation is that this algorithm almost constructs an integer solution, right? Like, if we look at the algorithm, then while it's going through this while loop, it's coming up with an integer solution, right? Like, it's setting these xi values to 1, not to anything between 0 and 1. And after our knapsack is full, we set all of the xj values to 0. That's also an integer solution. There's only one bidder who gets any allocation that isn't integer, right? It's this guy who was the last person who couldn't entirely fit into the knapsack, and so we kind of stuffed him in fractionally, right? This bidder I. And so one thing you might think is, okay, this algorithm almost works for us. It almost comes up with an integer solution. It provides a solution in which everybody except for one person, bidder I, receives a fractional allocation. What if I just skip that step? What if I just don't give out that fractional allocation? Right? Might that already be an approximation algorithm to our problem? And the answer is no. And here's sort of a simple way to see it. Suppose we have a knapsack whose size is 10. And we've got 2 bidders, and one of the bidders has size 10 and value 10. So he could fit into the knapsack, but if we put him in, there'd be no room left in it. And we've got another bidder whose size is only 1 and whose value is 1.1. So he also fits into the knapsack with 9 more units of space to spare, but there's not enough room for both bidders in there. And so the optimal value of this knapsack problem is obviously 10, right? I can only put one of these 2 bidders in, and so obviously I'll put the one that has value 10 in, not the one that has value 1. But if we consider running the fractional knapsack algorithm and then just forget about the guy who receives a fractional allocation, we will receive a terrible solution, right? Because this value 1 guy actually has slightly higher value density than this value 10 guy. right? V2 over W2, right? 1.1 over 1 is strictly larger than 1. And so our algorithm will first allocate to bidder 2, okay? And then the fractional algorithm will try to fractionally allocate to bidder 1. But if we just throw away that fractional allocation, we will get a solution that only allocates to bidder 2, and it'll have value 1.1 instead of 10, almost 10 times worse than the optimal solution. And there's nothing special about 10. You could come up with this, an instance in which I wrote 100 instead of 10, in which case you'd get a solution that was 100 times worse, or 1,000 times worse, or 100,000 times worse, right? So somehow just running the fractional algorithm and throwing away the bidder who was fractionally allocated is not a good solution. It doesn't provide any finite approximation at all. Right? Somehow the problem is that the fractional portion of the solution could have actually been like almost the whole thing. Like it could have been that almost the whole knapsack was filled with some fractional bidder, and we cannot afford to leave it off entirely. And so with that understanding in mind, let's try one more time. Okay, so here's an algorithm, and we'll call it greedy 2 because it's our second attempt. And it's going to be very similar. So again, we'll start by sorting the bidders in decreasing order of their value density. And again, we will greedily construct a set of winners. We will iterate over the bidders in order of their value density, and we will add them to our solution if they fit. Okay? And eventually we will, get to the first bidder I who doesn't fit into our knapsack, at which point we'll stop trying to construct this part of the solution. Okay, and if we just stopped here, this would be sort of the algorithm that we just discussed that doesn't work, right? We can't fractionally allocate anyone at this point. But what we're going to do now is we're going to check whether the welfare obtained in this solution is bigger than the value of the first person we didn't allocate. Okay? And if it is, if the cumulative value of everyone we've allocated is actually bigger than the value of the first person we didn't allocate, then we'll just output our greedily selected solution S. But if it is, we'll throw away S, we won't output it. And instead, we'll output a solution that consists of just one bidder, the bidder who by himself reported the highest valuation amongst all of the bidders. Okay, so that's the change. We either output this greedily selected set, or we output a solution that only contains one bidder, the high bidder. And so I want to claim that this second modification of the greedy algorithm actually solves our problem. It's a 2 approximation, and it satisfies this monotonicity property that we need for truthfulness. Okay, and so let's establish those 2 properties. So the first thing I want to claim is that this algorithm is a 2 approximation. It is guaranteed, no matter what happens, to output on any instance a solution that obtains at least half of the welfare of the optimal integer solution to the knapsack problem. And we're going to prove this by comparing the solution that it outputs to the optimal to the optimal fractional solution, which we know something about. Right? Because by construction, if we look at how this set S was greedily constructed, right? It is exactly the way that the optimal algorithm for the fractional problem begins, right? It has allocated exactly the same people that the fractional algorithm would have fully allocated. The only difference is that the fractional algorithm would have also given a partial allocation to bidder I. Okay? So this is just to say that for any bidder J who didn't end up in this greedily selected set S, and who wasn't this first bidder I who didn't get allocated, any such bidder actually also received nothing in the optimal fractional solution. And what that means is that if I look at the sum of these 2 values, the sum of the values of the people who got allocated both in set S and fully allocated in the optimal fractional solution, plus the value of bidder I, right? Bidder I might have gotten partially allocated in the optimal fractional solution. Because nobody else got allocated in the optimal fractional solution, this sum is only bigger than the optimal fractional solution. In fact, it's strictly bigger than the optimal fractional solution because bidder I wasn't fully allocated in the optimal fractional solution. And in particular, it's also bigger than the optimal integer solution because the optimal fractional solution is only bigger than the integer solution. And so in particular, I've got two things that sum to something that's more than my benchmark value. If I take the maximum of those two things, it's got to be at least half of my benchmark value because there's only two things in the sum. And what does my algorithm do? Well, it outputs the maximum of the value of the people in this set S, or the value of the guy who's got highest value, which is by definition only larger than the value of bidder I. And so that's it. The solution output by this algorithm has objective value that is at least half of the optimal objective value. And so it's a two approximation algorithm. And the only thing left to establish is that not only is this a two approximation algorithm, but that it satisfies this monotone non-decreasing property, this property for every agent I. That if they raise their bid, they can only go from winning, from losing to winning. They can never go from winning to losing. And if we can prove this, we will have established that there is a dominant strategy truthful two approximation algorithm for the welfare maximization problem in Knapsack Auctions by using the payment rule that we derived last class. Okay, so let's just finish this off. So first, let's fix some notation. Okay, so for any instance of the problem, for any vector of weights, and for any vector of valuations for all of the bidders, and for any agent I, and for any misreport VI prime that agent I might consider reporting, where VI prime is bigger than VI, I want to write V prime just for the vector of valuations that results if bidder I unilaterally misreports VI prime. And I want to write T for the solution that our greedy algorithm gives when bidder I truthfully reports. And I want to write T prime for the solution that our algorithm gives when bidder I misreports his valuation upwards. And just to reiterate the thing that we need to show, it's just that if bidder I is one of the winners in solution T when he bid truthfully, he should still be a winner when he misreports upwards. This is what the monotonicity property means. And towards showing this, I want to consider the sets S that are constructed greedily while we run this algorithm. Remember, the solution actually output at the end, T, doesn't have to be the same as S, because in the last step of our algorithm decides to either output this set S or to output this singleton set containing the highest bidder. But I want to talk about these sets that are maintained in the algorithm, and S will be the name of the set that's maintained when bidder I reports truthfully, and S prime will be the name of the set that results when bidder I misreports his valuation upwards. And first, I want to observe that if bidder I is in this set S, then he's also in this set S prime. And this is easy to see, because note that these sets S were constructed greedily by just sorting the bidders in descending order of their value density and picking the largest prefix of bidders whose total size was less than the budget. And note, by misreporting your value upwards, the only thing you're doing is you're increasing your value density. And so you're only moving yourself forwards in this sorted order. And so if you were in the prefix of bidders that fit in the knapsack in the original sorted order, and then you move yourself forwards in the sorted order, you're still in the prefix that fits within the knapsack because you only moved yourself upwards. And so if a bidder I was in this prefix X, was in this prefix S, he's still in the prefix S prime. And so we've already established then that if the algorithm outputs as its solution the set S, then it satisfies this monotonicity property. Right? Because if bidder I was in this set S already, then by raising his bid, he's only increased the value of the set S. And so if before his misreport, the algorithm output the set S, it'll still output the set S after his misreport because he's raised the value of the set S exactly in proportion to his misreport. And the only other case to consider is when the algorithm doesn't output the set S, but instead outputs the bidder who has the highest value, okay? But in that case, it must have been bidder I that had the highest value. And if he misreports up, then he's still the bidder with the highest value, and he will still be output. And so in that case as well, misreporting his bid upwards cannot cause him from becoming a losing bidder when he was previously a winning bidder. And so that's it. We've established that there exists a polynomial time 2 approximation algorithm for the knapsack problem that also makes truthful bidding a dominant strategy. All right. So I'm going to stop the recording now, but I'll stick around for a couple of minutes in case there's any questions.